Integration. So integration is just a reverse of differentiation, just like it's the inverse function of differentiation essentially. So what we're doing is, important thing is you know what's going on, and just make sure that you have like a and b as the upper and lower bounds. Remember, it's going to be b minus a, so make sure to keep it in the correct order, and make sure to put the dx at the end. That's really important, because if you leave that off, you won't get the mark for it, unfortunately. Okay, in terms of summary books, these are the formulas that you'll have on your formula sheet. It's also useful, just like with the formulas that we had for differentiation, just to write a couple of the formulas which might be a little bit more trickier to kind of talk about. Another thing that you can do is, when we're looking at this, remember that for the log, you'll always have that like modulus outside. So it's really important that we know to reject the modulus, and it's basically based on what the values of x can be for that function, and often it will tell you, and then you can just kind of guess from there, or not guess, but like kind of reason from there which side you have to take. And this is just a slide to say make sure you don't forget the plus c, because that's really important, because if you forget the plus c, they won't give you the mark. The only exception to that is like the thing of an versus the derivative. The antiderivative. If they say the antiderivative, you must put the plus c. If they say an antiderivative, technically plus c could be 0, right? So you could technically also just put no plus c, and it would still be the same thing. But I would say you can just always put the plus c to be safe, because even with an derivative, in an antiderivative, putting the plus c won't make you be wrong. Cool. Okay, let's talk about the process of integration by substitution. So there's a number of, let's say, tools that we have in our belt for integration. So there's substitution, we have by parts, we have by recognition, which is kind of the sister to by parts, and then we have also, we'll have the integration like using our like y-axis as well in Spec, and then we'll have integration using our circular functions, which is kind of like a special part of the integration by substitution, because circular functions can be funky. And also circular functions, like using the circular function rules as well, can be really helpful. Cool. All right. So let u is often very helpful in the terms of looking at like polynomials. So what we want to do is step down in power, okay? So the u will always be the one which is bigger, and the du dx will always be the one which is smaller. And it's okay if like you kind of miss which one's which. Over with practice, you will get better at kind of identifying which one you need to substitute and which one is the du dx component. What I look for in a question when I consider using this is, can I see the function and can I see the derivative in the same equation, and can I use that to my advantage? In a question where they have a denominator, which is a function, often the denominator will be the u, so that kind of gives it away a little bit. In terms of the steps, so we just let one of the parts equal to u, we need to find the du dx, and then we need to rearrange to kind of plop that into the equation as well. And then we put that in, so we convert the term. So if you have a definite integral, what that means is you don't have to convert back to x. But if you have a indefinite integral, what that means is you have to convert back to x, because remember, they want it in terms of x, not u. But that's, we'll talk about that when there's a question on it. But essentially, if you had like something that was in terms of x, so something in terms of x, you'd have to convert back to x. But if you have like terminals, right, so definite integral, you don't not need to convert, because you can just sub in the terminals, and it's a like it will be a number, right? And even if you convert back to x and try to sub in the number, it'd be the same thing. So you can just do that straight, but you need to convert back for this one. And then you can just solve for u and then sub the original back in. So you put in the u's, give yourself an integration which is actually easy to do, and then you can kind of put u and x back in after that. A special one is when we have like a linear. So what you do is you just make x equal to whatever the linear thing is, and then you make du dx equal to 1, because 1 times anything is just going to be the anything, so we can always use that, which is helpful, right? Because if you have something like root 4 minus x, we can definitely use that there, because we can say u equals to 4 minus x, and du dx just equals to 1. And now suddenly you have this, you've simplified this just to root u instead. So it's really nice. Cool. Alright, so let's talk about this question. I'll pop this question into the chat because I think it's a really good question to actually have a go at together. And I might give you maybe like, I don't know, like 10 seconds to kind of think about on your own of what you might do here, because I think it's really important for this one, and then because it tells you the substitution as well. So I might give you 20 seconds to just have a think what you might do and what you might consider. Okay, so hopefully you had a bit of a think about the general steps you might take and what you might do here. So it tells you the substitution straight away, which is actually really nice of them. So they want you to evaluate this. So because we're letting x equal to 2 sine u, we can kind of substitute that in. So we'll have, let's just kind of work out what this is first. So root of 4 minus 2 sine u squared, right? So what that's going to be is it's just going to be root of 4 minus 4 sine squared u. And this will look familiar to you because remember the cos squared x plus sine squared x will equal to 1. So if we kind of rearrange that and put a u in, we'll know that cos squared u will equal to 1 minus sine squared u, right? And we can just take out the 4 at the front there. So we're just going to get root 4 of cos squared u here, which means we're just going to get 2 cos u. So because this is just the positive root of it, we don't need to be concerned about the plus or minus, because it's not to say, like, it's not saying that x squared equal to cos squared u. It's literally rooting whatever it has in there, right? Just like the root of 4 squared is just going to be 4 rather than plus or minus 4, because the root is always going to give you the positive result. Okay, so we get 2 cos u, right? Okay, so then in terms of our du dx, what we're going to get is that this is going to be our, so in terms of our 2 sine u, right, we're just going to derive that, and the derivative of sine u is just cos, let me just put, because we have it in terms of u right now, so I'm just going to rearrange first before we jump ahead to that. So our x is going to equal to our 2 sine u, so therefore our dx du rather than our du dx is actually going to be equivalent to 2 cos u, right? Because the derivative of sine is just going to be cos. So then what we can do from there is actually kind of look into it a little bit further. So now we know our du dx is now going to be 1 over 2 cos u. Yeah? Okay. So then when we try and actually put it in and put it into the equation, right? Because we've gone from something which was we've gone from something which was 2 cos u before, and now we're going to try to make it to look like what we want to work with, right? So in terms of trying to find du, let's put this in now. So we'll say the antiderivative of 4 minus x squared, right, dx is also going to, so we don't need to sub in the terminals for this one, fortunately, so that we don't need to like explore it too much. So what we can actually do here is, because we have this dx kind of component here, what we want to do is, it's just like when you it's just like when when you're like, when we try to do the parametric differentiation of like the dx over du will be equivalent to our dx dt times our dt du. It's just like that. So what we're trying to do here is something quite similar, except we want our x component to be at the top, right? So when we're trying to do this, what we can try and do is, we'll put this in, so we have this 4 minus x, right? Because we'll have our we'll have our cos component here. So we'll have, this is going to be equivalent to 2 cos u, right, dx. And then we need to take care of our dx component as well, and we need to care for what's kind of going on with that component. So if we kind of look up to here and try and figure out what's going on, we can know that we have our x equaling to our 2 sine u, and therefore we'll have our dx du equaling to this equation. So what we can apply here to kind of get rid of that is instead go back to this one. That's not, sorry. Let me go back to the pen. Cool. Alright, so then we have our dx du here, and then what we're going to kind of substitute in is our u component. So what you're trying to do is actually make your du component the subject here, because what you want to do is you want to get rid of the dx component, right? So what you're going to do here is, instead of putting this in, you're going to rewrite this as dx equals to 2 cos du. Now that's a bit of dodgy maths, so like I think that it's better if you can write it without writing this statement, but if this statement helps make it more clear, you can always write it and then just rub it out. So then what you do is you can now put that in, right? Because now I'm going to write that. Oh, why'd that do that? Oh, sorry. Just need to rub it out. So I just need to put that in, so that will be cos du. So we can put that into there, so that will be 2 cos u du. So then from there onwards, we can kind of make it a bit simpler. So it'll be equal to, equivalent to 4 cos squared u du. And then we can kind of utilize the rules that we know. So we know that cos 2x is equivalent to 1 minus cos squared x, right? So we can kind of utilize this rule over here. So we can say that, therefore we'll have that cos squared u will just equal to, 2 cos. So it will just equal to 1/2 of 1 minus cos 2x, right? So when we kind of put that across, we'll have that's going to be 1 minus our cos 2x. So therefore we can kind of replace it with 1 plus our cos 2x. And therefore we can kind of replace it with what we have so far. X minus 1. So we can kind of replace it with this. So we'll have, this is going to, is there enough space? So it's going to be equivalent to just saying that it's 4 times 1/2 of cos 2x dx, right? So then we can kind of simplify that and just kind of simplify that down. So it's just going to be 2 cos 2x dx, right? Or 2 cos plus 2 dx. This is getting really messy. I'm going to just rub, I'm just going to rub all of this out and then rewrite, because there's not enough space for this, all of this to be on the same page. Okay, amazing, cool. Alright, sorry about that. There's just not enough space and everything's kind of getting munched together. Alright, so we kind of ended up with saying that this was equivalent to 4 cos squared u dx, du, sorry. And therefore from there we can kind of sub in our thing that we were talking about up here. So it's going to be equivalent to 4 times 1/2 1 plus cos squared 2u du. Okay, that's so much better that we can have space and actually see the working out. So 2 plus 2 cos squared 2u du. So what we're going to get from there is 2u plus, so when we anti-differentiate for cos, right, so essentially it just turns into sine, but because there's a coefficient out the front there, the 2 kind of gets taken away so that it reduces itself. So when we go from something like cos 2u and we try and differentiate that, that becomes 2, like negative 2 sine 2u, right? So we don't really need to worry about the negative too much, but for this one, we just know that it basically the coefficient comes out. So we can kind of divide by the coefficient and it's perfect. So we'll just end up with cos 2u, sine 2u du. Alright, cool. So now we have to substitute back the x in. So our x was 2, our x would have been x over 2 equals to sine u, so our u would have equaled to sine inverse x over 2, right? So we're dealing with this sine inverse x over 2, so what we're going to get here is 2 sine inverse x over 2 plus our sine inverse, our sine of 2 times our sine inverse of 2 over u. Sine inverse x over 2. Alright, so that's what kind of we can get from there. That's going to be our overall equation. So then we also need to add the plus c, because if we don't add the plus c, this will all be for naught and we won't get the correct answer. So after we do this, then we can kind of figure out what's going on from that. So this next step isn't really more calculus stuff, it's more kind of just like circular function stuff, and I guess it's a good thing to talk about and like talk about how we can rearrange this. So let's kind of disregard the first part for now and we can kind of take it all along the end. So let's just kind of consider this part first. So we substitute that in. So what we do is we can just turn that into 2 sine of our inside angle, so sine inverse x over 2 and cos of sine inverse x over 2. Right? Cool. Alright, let's rub it out all one more time. So that we, oh yes, let's erase all ink on slide. Actually, that's quite smart. Cool. Alright, and then let's do this one more page of writing for this. So this is a really long question. If you had got this question, it'd probably be worth like 5 or 6 marks, honestly. And I think it would be broken up a little bit more into its individual parts. But so far that we've gotten that this is equivalent just to 2 sine inverse. Oh my gosh, I can't write. Let me try that again. Okay, so ink, and then let's go to pen. Alright, so it's going to be equivalent to 2 sine inverse x over 2, and then we said plus, it was sine 2, it was 2 sine, yeah, and then it was sine 2 of sine inverse x over 2, like that. Cool. Alright, so let's focus on this second segment right here, what the sine inverse x over 2 component equals to. So if we focus on what this is equivalent to, this would be equivalent, like we were talking about, to sine inverse x over 2, so 2 of that times by cos of sine inverse x over 2. Now, we can apply our knowledge here of what sine inverse x over 2 is. So sine, once again, is opposite over adjacent. So if we made opposite here and adjacent here, we would get that this is going to just be x squared minus, oh sorry, wrong way around, 2 here, x over here, we would get that this one is just going to be 4 minus x squared, right, as the kind of the adjacent side to the angle up here. Right, so therefore we can kind of rewrite this whole thing as 2 sine inverse x over 2 plus of our, so we'll have our 2 of our sine inverse x over 2. So we'll have our 2x over 2, right, because it's the sine of the sine inverse, right? And then we'll also have, so we have plus c at the end here. Oh, sorry, plus c at the end here. And then we'll also have this component as well, which is going to be our root 4 minus x squared over 2, right? So then if we kind of write it out and simplify it and make it all in all, we'll end up with 2 sine inverse x over 2 plus x root 4 minus x squared over 2. Okay, and then plus c. Make sure to add the plus c's. Alrighty, cool. Sorry, that was a really complicated question, but I think it's really worth doing. So just kind of note that question down and put it into your bound notes or have it somewhere to have and peruse. Alright, this one is a lot more straightforward, and essentially all we need to do is just so we need to recognize which one has the higher power and what's going on. So often the one included in the function is the one we want to let u. So we have let u equals to x squared, so du dx will just equal to 2x. So we can kind of manipulate this into 1/2 2x sine x squared dx. So what we're going to get here is it's going to just be a half, right, of sine u, and then we're also going to have du dx, right, because we're replacing the 2x with du dx times bx, and you can see those two cancel out, right? So therefore what we're going to get here is it's going to be a half of sine u du, which is just, so remember cos goes to negative sine, so if we anti-differentiate sine, it'll go to negative cos, so we'll have a half negative cos u, right, plus c, and then we can just substitute that back in. So we'll have negative a half of cos 2x plus c. Yeah, that's right, cos not 2x, cos x squared. Let me rub that out. Cos x squared plus c. Cool. Awesome. Alright. Okay, so these are some partial fraction laws. I won't talk you through them because you can read. So just make sure you have these somewhere in your notes. That's really the only thing I wanted to highlight on this slide. Make sure you have it somewhere on your notes because it's really important for you to read and know how to do these. Okay, integration with trig, we've already done a little bit of this already, but essentially if you have even or odd powers, so what you want to do is essentially when you look at a trig thing with sine and cos all together, what you want to look for is which one has the bigger power, and you want to make everything the same base, and you also want to look for which one has the bigger power as well, and then you can use that substitution with u to kind of get rid of it. So we split the power, we can use sine squared plus cos squared equals to 1, we can use double angle formulas, etc., and then we make 1 equal to let u equal to the trig of the opposite trig of the odd power, or the one that has more powers, and then you can kind of substitute whatever you have in for the sine x or whatever, and then you can just solve. Cool. Alright, if we have even powers, what you do is you just use these formulas. So you're using like cos squared x sine squared sine 2x and sine kind of these types of formulas. So you're using all these ones are the double angle formulas, right? Oh, sorry, these 3 are the double angle formulas, and this one kind of just comes from the cos squared x plus sine squared x formula, so we can use that as well. Equals sine squared x equals to 1. So those are the formulas that it's derived from. Alright, let's go through this question. So first of all, we need this to be the same base, so what we're going to change this into is 2 sine 2x cos 2x cos 2x, right, dx. And then what we're going to get is sine 2x cos squared 2x dx. Alright, so we see that this one is alone and this one has squared power. So we have odd powers here if we added them all together. So what we're going to do is we can let u equal to cos 2x, right? Because this one is the one that looks like has more power on it, and this is lonely by itself, so we're pretty happy to just do that. So therefore du dx is going to equal to negative 2 sine 2x, right? We have the 2 already there, so we're happy with that. And then we just need a negative, so we can pop a negative out the front, right? And then we'll just have cos squared, so that's u squared du dx, so our negative 2 sine 2x times our dx, right? So that's going to just give us negative u squared du, which is going to give us that's going to be equivalent to negative a third u cubed plus c, which is equivalent also just to saying negative 1/3 of cos cubed 3x plus c. And just as a kind of a quick note to also note this in your thing, just for anybody who has some TN, there's shortcuts for both calculators, but for anybody who has the TN Inspire in terms of like the calculator kind of hacks for it, if you just go to, so if we pretended to type in this one, so if you kind of go to shift and then plus, it will give you the anti-differentiation one, and by doing that you're able to just pop in your equation, so you don't have to kind of go menu blah blah to kind of get your equation that you're trying to do, right? So from there you can kind of, so it was a lot quicker and we can kind of pop that into our calculator like that. All right, so then what we can kind of do after that is, so we see that this gives us our kind of our x squared component, right? So what we'll have is this, so we'll have this like kind of this component of what we're trying to do. So you can kind of change what that looks like as well. So in terms of our cos cubed x, we can kind of rearrange that into like a bigger formula as well. It's kind of up to you what you want to do, but you can just leave it like that as well. It's kind of up to you what you want to do from there. Okay, cool. So then integration by parts. When we do integration by parts, there's kind of two ways to do it. So there's the by parts way, or there's the by recognition way. By parts was only introduced this year, and it's essentially kind of the integration form of the product rule. So what you do is you use this thing like, use that kind of like acronym. So we have log, inverse, circular functions, algebraic, trig, and then we have exponentials, and those are kind of the order of the functions that we go with. And you make one of them a function which you're going to differentiate, and you make the other one the one that you integrate, and then you kind of just use this formula and sub that in. Okay, for integration by part recognition, so this is kind of a simpler type of one, I would say, is they actually ask you to differentiate it first, and then you integrate based on the differentiation you already have. Cool, so let's talk about it. So they want us to show that this is equivalent to this, and then hence evaluate the area enclosed by this graph and the two lines. So if we have f dash of x, and that's going to be equivalent to, so we diff the first, keep the second, so I'm just going to say that's 3 tan inverse 2x, right? And then diff the second, keep the first, so I'm going to say that's going to be 3x, and then it's going to be, so when we're anti-differentiating these, remember we just keep so we differentiate the top, so that will be 2, right? And then it will be plus 1 2x squared. So when we simplify that out, we'll get that that's 3 tan inverse 2x plus 6x over 1 plus 4x squared, as we need, right? Cool. Alright, so then we want to evaluate the area enclosed by this graph and the lines like this. So we already know that this, right, is the kind of the inverse function of what this is the derivative that we're working with. So straight away we can say root 3 over 2 to 1/2 of this 3 tan inverse 2x plus 6x 1 over plus 4x squared dx is going to be equivalent to 3x tan inverse 2x. Root 3 on 2 and a half. Right? Cool. Alright, so then the next thing we have to move over is this chunk of thing, right? So we're going to move that over and we're going to say that's root 3 on 2 and a half. 3 tan inverse 2x dx is equivalent to 3x tan inverse 2x root 3 on 2, 1/2, and then we can put that on there as well, so minus root 3 on 2, 1/2, 6x 1 plus 4x squared dx. Cool. So in terms of 6, the integral of 6x 1 over 4x dx, what that is actually equivalent to is if we let 1 plus 4x equal to u, your du dx would have been 8x, right? So therefore we can kind of substitute that back in so that this is 8x. So essentially all we needed to do to manipulate this is we can change this top part to ax, and we need to divide it by 4 and times it by 3. So 3 over 4. So then we can kind of change the terminals as well so we don't have to come backwards. And when we substitute the terminals in, so when we have root 3, we'll have, this is going to be root 3 on 2 squared, so that's going to just be 3 on 4, right? 3 on 4 times 4 is just going to be 3. 3 plus 1 is going to be 4, so we'll have this is going to be 4 at the top. We'll have 4, that's going to be 4 at the top there. And then when we do a half as well, so a half put into there is just going to be 1, right? 1 plus 1 is just 2. So essentially we're going to just end up with something like this. So we can kind of substitute that across and divide by 3 at the end, but we can divide everything at the end, like at the very, very end. So root 3 over 2, a half, tan inverse 2x dx is going to be equivalent to 1/3 of whatever this is. So we can also start substituting this in. So root 3 over 2, and tan inverse of root 3 is if we use our triangle. So that's root 3, that's 2, that's 1. So tan inverse of root 3 would be pi on 3. So it's going to be 3 root 3. Also, it's going to be root 3 on root 3 pi on 2, because root 3 on 3. So we'll have, this is going to be root 3 on 2 times pi on 3, right? Then we're going to have minus of a half going into that, so that's 3 over 2. And a half going into that, that's tan inverse 1, which is pi on 4. And then we're going to have here minus of our function that we're doing before. So we said that's 4 and 1. And we've replaced, we kind of took care of the top part. And we have 3 on 4 out the front here. And then we can kind of put in the stuff we had from before. So that's going to be 1 over u du, right? Okay, so we're going to end up with a log here. I'm just going to, I think I'll rub out this first section here to kind of talk about, to give us a little bit of space. So like that, and then if we want to talk about what's happening, oh, wrong one. So if we want to kind of talk about what's happening here, so this times that would just give you, so we'll get that the answer is going to be equivalent to, because the 3 can also be distributed across, right? So we're going to get that here, we'll kind of distribute the 3 across. So we'll get its root 3 pi on 2 minus pi on 8 plus, or minus this part, minus 1/4 of u, which is log e u, right, for 1. So that's going to be equivalent to saying, so if we times that by 4, so that'll be 4 root 3 pi minus 1 over, or minus pi, all over 8 minus 1/4 of log e, so that's log e4 minus log e1. Log e1 is just 0, so it's just log e4. Right? Okay, cool. And then we make sure to do the plus c. We could probably put plus c's all throughout, but yeah, you can just put the plus c's at the end as well. Okay, amazing. Alright, this one's using Lyautey, so we can first see that it's inverse circular function, and the other one we can just say this is one of the functions. So f of x, we're going to say that's going to be equal to cos inverse 2x, and then we're going to say g of x is just equivalent to 1. So remember from the components that we needed before, we needed f of x, g dash of x, and we needed the integration of this. So that means that we need to find the kind of the derivatives of each first. So we find the derivatives, so if we find f dash of x, that's just going to be equivalent to 2 over root 1 minus 4x squared. And then our g of x, when we try and differentiate that, so we want to be getting a function, g dash of x equals to 1, right? Because that's the one that we want to integrate. So g of x would therefore equal to x. And we don't really need the plus c stuff here, just because we're actually putting it backwards and putting it forwards, and we're eventually going to kind of put the plus c at the end. So if we kind of look at what we want is the integration of this, which is, so the integration of our f of x times our g dash of x dx is going to be equivalent to our f of x times our g of x minus the integration of our g, I think it was g dash of x. Yeah, so g of x times our f dash of x, right? Because that's the one that we're trying to do. So g dash of x, so it's kind of like how in the product rule, because it's g dash of x, f of x, plus f dash of x, g of x. So you just need every combination of those two. So this one had the dash, so this one doesn't have the dash, and this one's the f dash of x dx. Okay, so we can pop everything into here. So we will know that the integration of cos inverse of 2x dx is going to just be equivalent to f of x times g of x, which is just those two times together. So it'll be 2x over root 1 minus 4x squared minus the integration of g of x times f dash of x. So, sorry, that's f dash of x. So it's just cos inverse of x. So it's these two kind of combined together, the first one. So it's just going to be x cos inverse 2x. And then we're going to have our g, which is going to be just minus our g of x, which is our x, right, times our f dash of x, which is going to be just be 2x over root 1 minus 4x squared dx. Once again, we can let u equal to 1 minus 4x squared, so du dx would have equaled to negative 8x. So what we can have here is we can minus that from a fourth. So we'll have a plus c at the end here. So we'll have x cos inverse 2x, and then we'll have our plus c component. So we'll have we'll have plus 1/8 actually, plus 1/4. Oh, yes, plus 1/4, right? Because the negative is kind of integrated into there. And we'll have du dx at the top, which will cancel out with the dx, and then we'll just be left with 1 over root u du. Right? So in terms of 1 over u root du, let's put out the 1/4. So that's going to be equivalent to u to the power of negative 1/2, which means that we need to times everything by 1 over 1/2. And then we need to also increase the power by 1. So that's going to be root u now. So it's a half root u, and then we have plus c at the end. And then all in all, what we're going to get is x cos inverse 2x. So that's times by 2, so plus 1/2 root u, which is root of 1 minus 4x squared plus c. Cool. Okie dokie. Alright, So in terms of substitutions, this is kind of like the summary page for them. Just remember to step down powers, and you can use the special case ones as well. And just remember all the formulas that can be used. And really importantly, have this somewhere in your notes, the kind of partial fraction stuff, and kind of this formula and have that formula on your notes somewhere as well for integration by parts.